Good morning, everyone. So today, in the last class, we have talked about Legendre equation and Legendre polynomial. Today, we'll see some more properties of Legendre polynomial. The first one is the generating function of Legendre polynomial. So we say that 1 by square root 1 minus 2xt plus t square is equal to summation p n x t raised to the power n. It means that the coefficient of t raised to the power n gives you the value of p n x. So p n x means that when you expand p n x, for example, if you want to compute p1, p2, then it can be computed from the generating function. We are not going into the detail of the proof of generating function, but we will see many exercises based on the generating function. So to begin with, the first exercise says that show that Pn of 1 is equal to 1, then Pn of minus 1 is equal to minus 1 raised to the power n, and Pn of minus x is minus 1 raised to the power n Pnx. So now you can see that in all three cases you replace x by either 1, minus 1 or minus x. So let's try to do the same for the generating function. So let's try to put x is equal to 1. So if you put x is equal to 1, then it becomes 1 minus t whole square and minus half, so minus 1, and this is summation t raised to the power n pnx. So now coefficient of t raised to the power n on both sides gives you pn minus 1. So this is pn1, and the left hand side, if you do the geometric series expansion, then the coefficient is 1. Similarly, if you put x is equal to minus 1, it becomes 1 plus t raised to the power minus 1, and you replace x by minus 1. Now if you take the coefficient of t raised to the power n, then you will have the required answer. The next one, we have to show that Pn of minus x is minus 1 raised to the power n Pnx. This is little bit tricky. So this is my required generating function. In this generating function, what I will do is that I replace x by minus x and then z by minus z. Not at the same time, but you will get the two different relations. So if you replace x by minus x, then your right hand side is 1 plus 2xt plus t square minus half, and tn pn of minus x. So instead of z, it is t by minus t. And when you replace t by minus t, again the left hand side is 1 plus 2xt plus t square minus half, and this side is minus t raised to the power n, so which is minus 1 raised to the power n t raised to the power n and pnx. Now for both the cases, left hand side is same, so if you compare the right hand side, then t raised to the power n pn of minus x is minus 1 raised to the power n t raised to the power n pnx. So coefficient of t raised to the power n gives us pn of minus x is minus 1 raised to the power n pnx. So you can see that using the generating function, many problems can be easily addressed. Let's see one more. It says that p of 2m plus 1, where m is a positive integer, no negative integer, is of 0 is 0, and p of 2m of 0 can also be computed in this form. So again, using the generating function, we have to put x is equal to 0. So for x is equal to 0, this becomes 1 plus t square minus half, and this is tn and pn 0. Now if I expand 1 plus t square minus half, so 1 plus t square minus half can be written as summation minus half, then minus half minus 1, so n minus 1, so minus 3 by 2, so on, and minus half minus n plus 1. Then t square is there, so x raised to the power n, so t square raised to the power n and divided by n factorial. Now from each of the above term I can take minus common, so it becomes minus 1 raised to the power n. The remaining term would be 1, 3, 5 and so on goes to 2n minus 1. Then t raised to the power 2n. Denominator, because of 1 by 2, 3 by 2, you have 2 raised to the power n, n factorial. And now I can multiply both the sides by 2, 4, 6, 2n and 2, 4, 6, 2n. So if you multiply it, then it becomes minus 1 raised to the power n. Then the numerator becomes 2n factorial t raised to the power 2n. The denominator is 2 raised to the power n, one more 2 raised to the power n, so 2 raised to the power 2n, then n factorial, because this can be written as 2 times 1 dot 2 till n, so 2 raised to the power n dot n factorial. So this is n factorial square. So this implies that p of 2m plus 1, because it does not have any odd powers. If you compare the coefficient of x raised to power 2n plus 1 or t raised to power 2n plus 1 on both the side, p of 2n plus 1 of 0 is 0, and p of 2n of 0, it is minus 1 raised to the power n, 2n factorial, 2 raised to the power 2n and n factorial square. Let's discuss the last question. This gives us a recurrence relation. Recurrence relation means you will have a relation between Pn and its preceding terms, or Pn plus 1 its preceding terms. It's very important to remember the generating function as well as the recurrence relation. We'll see some exercises based on the recurrence relation also. But today we will only see how do we prove this recurrence relation, which says that n plus 1 Pn plus 1 is equal to 2n plus 1 x Pn x minus n Pn minus 1. So I will again use the generating function, and in the generating function you can see that I need Pn minus 1, Pn plus 1. So therefore, to have the different coefficient, I must differentiate with respect to t. So differentiate with respect to t and see what you are getting. So the left hand side is minus half, then 1 minus 2xt plus t square minus 3 by 2, then minus 2x plus 2t, and the right hand side is p and x remains as it is, so n t raised to the power n minus 1 and p and x. Now I need p and x on both the sides, so the left hand side I have to multiply it with 1 minus 2xt. So let's call it equation 2. So multiplying equation 2 by 1 minus 2xt plus t square, and see what you are getting. So minus half is there. Even for the minus half I can cancel this 2, 2, 2, and minus 1 I can take inside, so it becomes x minus t. So x minus t, then 1 minus 2xt plus t square minus half, and you multiply 1 minus 2xt plus t square, then summation n t raised to the power n minus 1 and p n x. If you want, you can use the generating function. So this becomes summation t raised to the power n pn x, and this is 1 minus 2xt plus t square summation n t raised to the power n minus 1 n pn x. Now comparing the coefficient of t raised to the power n, see what you are getting. So if you compare the coefficient, then the first term, it get multiplied by x, so has no effect on pn, so x and t raised to n pn x minus t raised to the power n plus 1 pn x. So coefficient of t raised to the power n is pn minus 1. Now if you see the right hand side, then the first term is 1 multiplied by n pn tn minus 1. So coefficient of t raised to the power n is n plus 1 and pn plus 1. Then minus 2x, and n is also there, and t raised to the power n, which coefficient is pn. Then t square, so this becomes n t raised to the power n plus 1. So I need the coefficient of t raised to the power n, so it is n minus 1 and pn minus 1. Please do verify by yourself. And now if you simplify it, then it becomes n plus 1 pn plus 1 is equal to x 2n plus 1 pn minus n pn minus 1. So that's all from today's class. In the next class, we will discuss the orthogonality property of the Legendre polynomial. Thank you.